Hello, this is Sandhya Nityanandan, and this is the final project of the coursework AEDG 6370. In this project, we implemented an AES 128 encryption and decryption system using a hardware software co design approach. The main idea behind this project was to offload the encryption task to the FPGA, which is much faster at performing these operations, while the HPS handles higher level tasks like key generation, reading user input, software based encryption, and validation. My part in this project was focused on the software side. I worked on generating a random 128-bit encryption key, reading the user's plain text, sending that data to the FPGA for encryption, and then decrypting the resulting ciphertext on the HPS to verify that the encryption was working correctly. My teammate Venkat worked on implementing the AES encryption module on the FPGA where the actual encryption happens. So, coming to the AES 128 or Advanced Encryption Standard with the 128-bit key, it is one of the most widely used encryption algorithm. It is symmetric, which means the same key is used for both encryption and decryption. AES works by taking a 128-bit block of data and performing a series of transformation in 10 rounds for AES 128, which includes substitution, shifting, and mixing of data. In our project, the FPGA performs the encryption operation, and the HPS is responsible for both the software based encryption and decryption for verification. The HPS is also in charge of managing the user's input, generating the encryption key, and confirming that the ciphertext generated by the FPGA matches what the HPS decrypts back to the original plain text. So, my role in this project was to handle all the logics in the software, from taking user input to interacting with the FPGA, and the final verifying the output through decryption. The goal was to verify that the hardware and software could work together seamlessly to perform AES 128 encryption and decryption correctly. So, this is the HPS main.c code. Here I have included several standard libraries like stdio.h, stdlib.h, stdin.h, and others to handle basic operations such as printing to the terminal, memory management, and random number generation. These libraries are essential for managing the input, output, and hardware communication in our code. Additionally, I have included hardware specific library like hwlib.h, socal.h to help interface with FPGA and HPS, which we'll use for memory mapped IO. Next, coming to the functions, I have written a small helper function which is called print hex bytes, which prints out the content of a byte buffer in hexadecimal format. This is helpful when we need to visualize the key, plain text, ciphertext, or decrypted data in a human readable format. Next is the AES definitions and S boxes. We define some constants here like AES NB for the number of columns in the state, AES NK for the number of 32-bit words in the key, and AES NR for the number of rounds used in AES 128 encryption. AES 128 uses 10 rounds for encryption. So, next main blocks are encryption and decryption. No, before that, we'll be having the key expansion function. This is the key expansion function which takes the original 128-bit AES key and expands it into multiple round keys. AES uses a key schedule to generate the key for each round. This function also applies the SBox and Archon transformation to the key during the expansion process. So next is the encryption block. So this is the main AES encryption function. It works in rounds with 10 rounds for AES 128. We start by applying the key to the initial state, which is add round key. Then for each round we perform substitution like with the function sub bytes. Then row shifting, which is shift rows, and column mixing, which is mix columns, followed by another key addition. After 9 rounds, the final round skips the mixed column operation alone but performs the other steps before the final add round key. So next is the decryption block. This is the AES decryption function which reverses the decryption process. It applies the inverse of each and every encryption operation like inverse of shift rows, inverse of sub bytes and inverse of mixed columns to the byte in reverse order. This process starts by applying the last row key and goes back to the round until the original plain text is recovered. So next we'll be coming to the memory mapped IO and FPGA communication. Here, this part of the code handles communication with the FPGA. We use memory mapped IO to send data to and receive from the FPGA. First, we'll be opening the /dev/mem file to get access to the memory. Then we use a map to the hardware register into the program's memory space. The FPGA's memory address are mapped to the specific pointers like key 0 pointer, PT0 pointer, etc., which are used to send the AES key plain text and receiver ciphertext. So, coming to the final output and cleanup. So, to conclude, the HPS is responsible for generating the AES key, handling user input, performing software based encryption and decryption, and verifying the output. The FPGA, on the other hand, handles the encryption. Venkat worked on the FPGA part where he implemented the AES encryption hardware module while I handled the software side. This project shows how hardware and software can work together to perform AES encryption and decryption efficiently, with the FPGA accelerating the encryption process and the HPS managing the overall logic and validation. Venkat will now explain the FPGA part, where he implemented the AES encryption module, handling the encryption process in hardware. Thank you.
FPGA hardware part, where we first import our files from our previous homework and just edit that previous files to modify for this particular project. So let's first open up the platform designer. So in our platform designer, we can see we have created four four keys, four ciphertexts, and one end and begin block. So we give different addresses for each of the buses, and once those are connected to the clock and the reset to the reset and export the conduct, and the S1 is again exported to the AXI master, we can go ahead and generate the HDL for this. When we see the template, we can see all our instances have been created and all the ports have been exported. So once we generate HDL, it must generate the HDL code without any errors. So once that is generated, we can go back to our main code. We have the AES core where the actual encryption is performed in this particular code, and we set the GHRD as the top module and compile the code. So let's compile the code. So we can see the code has been successfully synthesized, and we can see our resource utilization where we've used 5,979 ALMs is needed, and the combinational LUTs are going to be 9147, and the input output pins used are 368. So similarly, now we can go to our programmer, dump the code into our system. Once the code is successfully dumped into our system, we can go to the Terra term. We are using Terra term for this project because when we enter the commands into the monitor starts flickering. So let's so once the device has been mounted, we can go ahead, go into, so after giving the necessary commands, we can see that we are getting the expected output. When we enter the plain text, we are getting the ciphertext from the HPS and the FPGA which matches, and the plain text is again decrypted. This is the decrypted data after the software, so which matches whatever we entered. We can try another input. So we can see the original plain text and the ciphertext are matches, and we are getting the decrypted data. So this concludes the homework FPGA project. Thank you.